Greetings, geek students. I have a quick demo to show you using the exact same circuit that's described in your capacitors packet. I'm going to be using the LabQuest power supply that'll plug in here. Before I plug it in and send power to the circuit, I want to trace it out for you. So coming from positive, which is routed from the power supply, going to a 3-pin switch. It is called SPDT. That stands for single pole double throw. More on that next week. You go from positive to one pin of the switch. Then from the middle pin of the switch, we go to, instead of what's described in your packet, for this demo, I have a light bulb. And we know that a light bulb is ohmic, but very temperature dependent now from the Ohm's law activity. And then from the light bulb, I'm going to a capacitor, but a much bigger capacitor than the one that you will use for this activity. This is a 6800 microfarad capacitor. For your data collection, you'll be using the 100K resistor and the 47K resistor instead of a light bulb. And then you'll also be using a 10 microfarad capacitor. And then from the other side of the capacitor, I'm going to the negative pin, and the other part of the switch also goes to the negative pin. So what you'll be exploring and making precise measurements of are how the voltage changes across the capacitor. And as I stated before, a capacitor is truly a break in the circuit. The capacitor itself doesn't pass any electric current, but its effects can change where and when current will flow in a circuit. So it introduces these time-dependent effects. So if I flip the switch, the light bulb lights briefly as current flows to one side of the capacitor and then stops as the capacitor is so-called charged up. And then when I flip the switch the other way, the capacitor will discharge. So it's the change in what the capacitor is connected to that will allow current to flow through the circuit in different ways at different times. So the effect is transient. And that's one of the technical terms we'll be exploring, transient effects in circuits. So the light bulb never lights continuously. It just lights as current is flowing, and the current tails off. And one of the things you will explore is the nature of this tail off. So as you measure the voltage across the capacitor in different ways in the circuit, you will measure the curve of the voltage increase and decrease, or the charging and discharging of the capacitor. And it has a very specific shape that you'll use the analytical tools in Logger Pro to mathematically model. Here is the full circuit for this activity. Notice that we are using the regular voltage probe, not the differential voltage probe, and we are also using the LabQuest power supply. The regular voltage probe has no black box attached. Hello again, geek students. Here's an example of what you will see for the capacitors activity for Vernier. I'm going to open the file under the Physics with Vernier folder, file 24, capacitors. And this is set just to record voltage with respect to time, because we're only using the voltage probe and the non-differential voltage probe, just the one that has no box attached. And we're going to be measuring the voltage across the capacitor as it, quote, charges up and discharges. There's 2 pages programmed in this file. One of them is a data table that also has what's called a natural log plot. So the natural log of voltage, and we'll see what that looks like later. That's for the analysis, but I just want you to know to reach that, you press next. This is the main page that will record the charging and discharging of your capacitor circuit. Notice here that the potential is not 0 right now. What we do, remember, is we connect the probes of our voltage probe together, and then what we'll do is we will go to experiment and 0, and then our probe is zeroed out. So it's ready to accurately read what the voltage is. It's just like zeroing a balance. So now I'm going to connect across the 10 microfarad capacitor that's on the board. There's still a little voltage in there, but that's okay. And I have it connected exactly as in the picture that I presented right before this. And so what I'll do is I'm going to press collect, and the voltage is low, and then I'm going to flip the switch, and that puts the capacitor and resistor in series with the battery. And after enough time, I'm just going to stop it. So now I have a charging curve for the capacitor. And then what I will do is I will experiment, I'll store that run, and then I'm going to hit collect again. And now I have, after a little bit of time, I'm going to flip the switch down, and then that removes the battery from the circuit. And this is the discharge curve for the capacitor. There's little bumps and noise in this. It's not perfect, and that's because we're not using a perfect battery. The power supplies that we're using, the LabQuest power supplies, are very noisy. I invite you to use the 5-volt output on the desktop power supplies just to see how it compares. It's probably going to be a lot cleaner because those are nicer power supplies. And if you use a 9-volt battery, it would be perfectly clear. But for our purposes, the LabQuest power supply, even though it's noisy, is going to give us enough workable data. So what I'll do now is I'm going to store that latest run. So now that I have my data sets for charging and discharging for the 100K resistor in series with a 10 microfarad capacitor, I can model these curves and get some parameters. I'm going to do the discharging curve first. And I don't want to select this part because this is before I flip the switch. I only want to get the part after I flip the switch. So it doesn't have to be exact here. I just want to select from after the switch has been pressed. It doesn't matter the vertical selection, it just matters the horizontal selection. And I'll select a good chunk of it. And then I'm going to go to curve fit. I'm going to do, the discharger is actually run 2. And I'm going to use a natural exponent. And I'm going to try the fit. And that is a beautiful fit. And these are the parameters A, C, and B as described in the packet. So A times EXP, which is E to the minus C times T power plus a term B. And again, this is that base E of the natural logarithm. So E being 2.78 approximately. I'm going to press OK, and there is my first curve fit. The second curve fit, I'm going to select, this is the charging curve. I'm going to select a good chunk of that, and I'm going to go to curve fit. This was run 1, was the charging, and this one is inverse exponent. I'm going to try the fit, and also again a beautiful fit. The equation is slightly different, and again these were described in the previous videos I had made and in the intro to the lab handout. And here are the parameters we read off. And then I'll press OK. You can always, again, double click on these and you can make the fonts bigger. I'm going to make them a little bigger, might be easier to see in the video. And I'll make this one bigger. Appearance, let's go to 20 is good. You can always change colors and stuff. I'm going to move this around so I know that this is discharge and this is charging. And one thing that is incredibly maddening about this activity is this C is not capacitance. So in the algebraic equations, we use C to represent capacitance, but in this parameter, it means something entirely different. It is connected to the time constant of the circuit, and it's specifically 1 over this parameter C is the time constant of the circuit. And I would expect for the 100 kilo ohm resistor and the 10 microfarad capacitor that time constant is really close to 1, and that's what we're seeing right here. Now, the last thing, if I go to next, notice that this, if I were to look at this discharging, I can see from my run 2 here, discharge is in green, where the discharge is very exponential, I can actually do a linear fit. I'm going to do run 2, a linear fit. And this is actually a way we used to look at modeling
exponentials and natural logs, because you could do what's called a logarithmic scale, and instead of a curve, you would see a straight line. So that's what you see here. It works for the discharge. It's not working for the charging curve, because we'd have to arrange this graph slightly differently. But that's the other page for analysis in the analysis questions. So charging, discharging, and then you look at the logarithmic scale, and you'll also do this for another resistor. And if we cut the resistance in half, it's 47 kilo ohms instead of the 100 kilo ohms, you should be able to formulate a hypothesis as to what would happen to these charging curves and to the amount of time it takes to charge and discharge the capacitor.